Good day to all. We're going to be continuing our discussion on gas laws. First, we'll be invoking a new equation that relates density to our other parameters. Then we're going to be looking at why gases deviate from ideal behavior. Turns out that in real life, sometimes gases ain't so ideal. Finally, we'll be looking at our atmosphere, which is full of gases. We'll be talking about the different components of the atmosphere, both in terms of what gases are present and the different layers of the atmosphere. So let's jump into it. Recall last time we talked about how gases occupy about 22.4 liters under standard temperature and pressure. And as a reminder, what are standard temperature and pressure? STP, 0 degrees Celsius or 273 Kelvin, and 1 atmosphere of pressure. So kind of a cold temperature for us humans. 1 atmosphere of pressure, that's kind of classic. So here we have a whole bunch of different gases. We've got carbon monoxide and argon and helium and hydrogen and krypton and neon and nitrogen and oxygen and xenon. And notice that they're all about 22.4, give or take, liters under these standard conditions, 0 degrees Celsius and 1 atmosphere. So this works pretty well for most gases, for most ideal gases. And we'll discuss again in a little bit that sometimes these gases do deviate from ideal behavior. So now let's invoke density into the ideal gas law. So density is mass divided by volume. And a few things, remember mass, lowercase m, is equal to the number of moles of gas you have times the molar mass of said gas. If you multiply the two together, you'll get the mass. So we can rearrange this to get the number of moles that you have of a given gas are equal to the mass of that gas divided by the molar mass. So if we take the mass and we divide by the moles, the grams per mole of something, we'll get the number of moles. Okay, so there is relationship number 1. Relationship number 2 is PV, PV equals nRT. So now what we're going to do is we're going to substitute out moles in PV. So wham, substitution. There we have our new version of PV with mass divided by molar mass in place of moles. And now kabloomers, rearrangement. And we get this. So we get pressure times molar mass divided by our gas constant R and temperature is equal to mass divided by volume. Mass divided by volume, wait a minute, that's density. Voila. So there we have our last equation for our gas laws, the equation for density. So let's just quickly run through an example calculation of this. If you want to take a moment to pause and do the calculation, feel free to. Let's do this. So density is equal, again, to the molar mass of a given gas times the pressure divided by the gas constant R and temperature, absolute temperature. So here we have R in terms of liters atmospheres per mole Kelvin. The molar mass, we're looking specifically at helium. Helium is a cool 4.003 grams per mole. Temperature that we're looking at in this particular situation is 21 degrees Celsius, and our barometric pressure is 752 torr. So let's convert that to atmosphere so that our units align. It's about 0.98947 atmospheres. Okay, and that could be typical pressure at up at this elevation of Happy Valley, about 1,000 feet above sea level. So our density is going to be equal to our molar mass times the pressure, which is about 0.99 atmospheres, divided by R, 0.08206 liters atmospheres per mole Kelvin, times our absolute temperature, which is 294 Kelvin. When we do this and all of our units cancel out, we'll end up getting that the density is 0.164092. That's an excessive amount of units there, grams per liter. About 16 grams per liter. And it turns out that's a lot lighter than the density of just regular air. Helium is pretty light. Air has a lot more heavier components in it, like nitrogen gas, oxygen gas, etc. So as a result, helium is a lot less dense than air, which allows for balloons to float. Well, helium balloons, that is, to float. Neat. So take a moment here, just given what we just talked about, and see if you can predict which one of these, let's say they're all in a 1 liter box, which of these gases depicted in our Maxwell-Boltzmann distribution would have the greatest density? If you chose A, that's correct. Because remember, we can tell a lot about the relative masses of gases by looking at the root mean square speed, by looking at how the distribution is skewed. Remember, the greater the mass, the slower the gas. So gas A is the slowest here. It's got the slowest general distribution of speeds. You can use the root mean square speed to help quantify that. And since it is the slowest gas, it has the greatest mass. And since density is related to the molar mass, remember, the greater the mass, the slower the gas. Choice A for the win. All right, so now let's talk about mole fraction. Mole fraction is literally what it sounds like. It tells us what fraction of a given sample of gases, or it doesn't have to be gases, but in this case, since we're talking about gases, let's roll with it. So it tells us what fraction of a given sample are a specific gas. So the equation for it is the mole fraction is defined as this x sub a, and it's equal to n sub a divided by n tot, where n sub a is the moles of a given gas, a specific gas, like oxygen, or nitrogen, or xenon, or neon. And n sub tot is the total moles of gas. Now, by definition, if you add up all the different mole fractions in a given sample, they have to equal 1, because if you have a sample, if you add up the individual fractions, they have to add up to 1, otherwise, well, that'd be impossible. So another thing that we can use is this equation here, P sub A. P sub A is something called partial pressure. Partial pressure is the pressure being exerted by a specific gas, again, like oxygen or nitrogen or neon, etc. And we can either write it out as n sub A divided by n tot times total pressure, or we can just plug in mole fraction times total pressure. So if you look at a given sample of gas, if you want to know what pressure is being exerted by a specific gas in a sample, all you have to do is take the mole fraction of that gas and multiply it by the total pressure. So let's say that you have, for example, with the atmosphere is about 78% or so nitrogen. That means that 78% of the pressure being exerted from the atmosphere is from nitrogen. So if we're at sea level, we've got 1 atmosphere worth of pressure, 0.78 atmospheres are coming from nitrogen. Okay. P sub A is known as partial pressure, and so that A could be, say, O2, it could be N2. We can actually replace it with what the gas is specifically. But whenever you have uppercase P and then subscript, that refers to whatever specific gas you're looking at. So let's take a look at another way that we can report a concentration of gases using parts per million. Parts per million is useful if you have a very dilute gas, something that's not overly present in a given sample. So what it tells us is literally how many, for every 1 million molecules you have, how many of those are a given gas. So we can define it as ppm, or parts per million, are equal to the molecules of a certain gas for every 1 million molecules of gas present. We can rearrange this to get mole fraction times a million. So if you have the mole fraction, if you want to find the parts per million, just multiply it by a million, and voila, parts per million. So let's consider the mole fractions of gases in the Earth's atmosphere. Nitrogen is the most abundant, then oxygen, then argon, then CO2, then neon. If we wanted to put nitrogen in terms of parts per million, well, there's a vast amount of nitrogen in the atmosphere, but what we do is take the mole fraction, the 0.78, multiply it by a million, and this gives us 780,840 parts per million. So out of every 1 million molecules of gas or particles of gas out there, 780,840, most of them are nitrogen. So let's do this as a follow-up question. So let's say that the barometric pressure is 757 torr. What is the partial pressure being exerted from oxygen? So if you want to take a quick moment, pause, see if you can do that calculation. Let's get to it. So remember that partial pressure of a given gas is equal to the mole fraction of that gas times the total pressure. So all we have to do is take the mole fraction of oxygen, which is about 0.21, and multiply by the total pressure, which is 757 torr. And that gives us about 159 torr. So if the total pressure is 757 torr and oxygen is about 21% of gas, that means that oxygen is exerting 21% of that pressure, which is 159 torr. Okay, so on to our next part. Gases. Are they always ideal? Truth be told, no. Sometimes they are not so ideal. And there are a few key factors, 3 that we're going to be concerned with, that cause gases to deviate away from ideal behavior. Now, the reason why they deviate from ideal behavior, if we look at kinetic molecular theory and we think about the postulates of it, first of all, we assume that molecules of gas, ideal gases, actually don't have an appreciable volume. Truth be told, they do have a measurable size. They are taking up volume. That causes them to deviate a little bit from ideal behavior. We also assume that these molecules don't attract nor repel each other. They just have perfectly elastic collisions. And truth be told, as we know, molecules do have intermolecular forces. There is an attraction exerted between 2 different molecules. So let's talk about how this plays out and what conditions cause molecules to deviate from ideal behavior. So first, let's talk about intermolecular forces. And we have here 4 different molecules. And a question that I have for you is, which of these do you think would behave most ideally? Which do you think would behave least ideally? So intermolecular forces. We're assuming with ideal gases that there are no intermolecular forces. So if there are more IMFs, that means we have a less ideal bounce because, so let's take this down to super slow motion. As the gases are about to collide, ideal behavior assumes they just bounce right off of each other. But what actually happens is there's this moment of interaction before they bounce off. So, that in mind, take a second and see if you can identify the most ideal and the least ideal of these 4 different molecules. Let's see how we did. So, the molecule with the least amount of intermolecular forces is going to be the most ideal. So that's going to be this one here. This one here because it's more compact. And so remember, the more splayed out a molecule is, the more opportunities for interactions with other molecules it has. This one's a more compact molecule compared to these other ones. It has, all these have pretty similar masses, but A and B only have London dispersion forces. In terms of comparing A versus B, B has less London dispersion forces because of its compact size. So which would behave least ideally? So the most amount of intermolecular forces is going to be the least ideal gas, which is going to be this molecule here. It's got dipole-dipole interactions available. It also has 2 sites available for hydrogen bonding. It has those 2 alcohol functional groups on both ends. The other things that contribute to gases behaving less ideally are temperature and pressure. So how does temperature fall into place? So low temperature is least ideal because at low temperature, gases are moving more slowly. They have more or less kinetic energy. So the more slowly they're moving, the more time there is for them to interact, the less ideal the bounce is going to be. Whereas at high temperatures, the gases are moving around fast. They can bounce off of each other more ideally. So remember, more interactions means less ideal. In terms of pressure, what's more ideal? High pressure or low pressure? So under low pressure, gases are kind of more spaced out. They're not as crammed in. They're not as stuck dealing with each other. Whereas at high pressure, so let's say that this video window here is our box. If we're at high pressure, oh, there's not a lot of space. These molecules are being crammed together and they're interacting more. So in terms of pressure, high pressure is least ideal. Low pressure is most ideal. Remember, more interactions is less ideal. Okay, now let's talk a little bit about the atmosphere. And where we're going from here is we're going to talk eventually about climate science. We talked a little bit about it earlier in the semester. Now we're going to be using the tools that we've been developing in our Chem 110 toolbox and using that to understand what's happening in our atmosphere and with our climate. So we already talked a little bit about the Earth's energy balance. Now let's talk a little bit more about the atmosphere. So the atmosphere is a collection of gases that are held in place by the Earth's gravity. And here we have an extensive list of the makeup of the atmosphere. Nitrogen, again, is most of the atmosphere, 78% of gas in our atmosphere is nitrogen, then oxygen, and then the other ones are a lot more trace. So argon, carbon dioxide, neon, helium, et cetera, et cetera. Now then, here we have a boss fight question. This brings together a whole bunch of different ideas. So let's say that an average human breathes in about 3,023 grams of oxygen every day. So if that's the amount of oxygen being breathed in, approximately how many liters of dry air, so air including oxygen and nitrogen and everything else, does an average human breathe in on a daily basis at 1 atmosphere of pressure and 25 degrees Celsius? So take a moment, pause the video, and see if you can get the answer to this pretty complex question. All right, let's go through the solution. So what we're trying to do here is we're trying to find a total volume. So we're trying to relate pressure, we're trying to relate temperature, we're trying to relate an amount of stuff, moles we'll see eventually, and we're trying to relate volume. Whenever we're trying to relate an amount, a pressure, a temperature, and a volume, when in doubt, I should have had this queued up. When in doubt, piv-nerd it out. First, we need moles. So we'll take those 3,023 grams of oxygen, we'll divide by the molar mass of oxygen, and that ends up being 94.5 moles of oxygen. But is oxygen the only gas present in our atmosphere? Thankfully, no, because if it was just oxygen, well, the atmosphere would be very, very, very combustible. But also, oxygen is really reactive. We don't want to have that much oxygen. You do want oxygen, just not all oxygen. So we need to figure out how many moles of gas there are total in dry air. And to do that, we can use this relationship. We can use the fact that the mole fraction is equal to however many moles of a given gas divided by the total moles. So we'll plug in what we know here. Oxygen, or the atmosphere, is about 21% oxygen, so our mole fraction, 0.209. And then we're going to set that equal to 94.5 moles of oxygen that are breathed in a day, divided by the total moles. So we end up getting that we breathe in about 452 moles of air, including oxygen, nitrogen, argon, carbon dioxide, neon, et cetera, et cetera, et cetera. Now we can plug all this into piv-nerd. So 1 atmosphere of pressure times the volume is equal to the 452 moles times 0.08206 liters atmospheres per mole Kelvin times the temperature in Kelvin, 298, and we end up getting 11,050 liters. That's a lot. That's a lot of air. And that is about the average amount of air breathed in by a human on a daily basis. Considerable. Okay, so looking ahead, the atmosphere is broken down into 4 regions. Those regions are the troposphere, that's where we live in. Then moving up, we have the stratosphere, then the mesosphere, then the thermosphere. So what is it that defines the cutoff points between troposphere, stratosphere, mesosphere, and thermosphere? So if we look at this plot that we have here, the temperature is given, or the average temperature is given, and we can see that as you move up higher and higher and higher in the troposphere, it gets colder and colder and colder. So there's less kinetic energy in these molecules as we move up, and it gets colder. But at one point, we hit this inflection point where suddenly the temperature, the average temperature, starts getting greater. And that's where we've entered the stratosphere. And then eventually we'll hit another inflection point where things get colder. That's where the mesosphere begins. And it's going to keep getting colder until eventually get to the thermosphere, whereas you go up higher in the thermosphere, the temperature actually increases. So these inflection points are what define the different regions of the atmosphere. And these temperature fluctuations are actually due to reactions. So For example, the ozone cycle is what creates that increase in temperature in the stratosphere. That's where the ozone layer is located, and the ozone transferring around between O3, O2, all this stuff, those reactions release heat and cause that warming. Up in the thermosphere, the reason why it gets higher is actually because of ionization. So we have these ionizing reactions that take place, and that's what causes that greater heat profile. Now, the other thing that's kind of interesting about this is these reactions, these ionizing reactions that take place up there, there's interactions with the Earth's magnetic field, and what they end up creating is this really cool, vibrant display of lights called the aurora borealis. These are caused by the ionizing reactions in the thermosphere. Neat. Okay, so thank you very much for watching, and I hope that you have a wonderful day.